أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. In today's lecture we will talk about the mathematical formulation of the first law of thermodynamics. Moreover, we will also discuss the modern concept about heat. This is actually the topic that has been taken from the course of thermodynamics, course outline of thermodynamics, and the course code for this course is PHY331. And the basic objective of today's lesson is to revise and understand the first law of thermodynamics, that is actually connected to the law of conservation of energy. We need to develop the mathematical formulation for the first law. How we can put some of the thermodynamic variable on one thermodynamic coordinate on one side of the equation and some on the other side of the equation to make it balance and apply law of conservation of energy. And at the end we will discuss some old concept, revise the old concept about the heat that was actually the part of last lecture, but we will revise it today again, and also develop the new concept about heat, that how the new concept has been introduced and what was the experimental background for developing the new concept. So the first part is devoted to the understanding of the first law of thermodynamics and the mathematical formulation of the first law of thermodynamics. For this purpose we need to consider two systems that are separately or independent from each other, and we need to find out the work done in both the systems. So we need to find out the change in internal energy and with the help of diathermal walls. And in one case we need one of the paramagnetic solid has been inserted in a liquid helium, and we need to find out the change in the paramagnetism or the change in the magnetization of the sample. So the first case, here is a cylinder system. A gas is enclosed inside the cylinder. There is a piston on it, and the piston is flexible or movable, and above the piston there is some weight placed or maybe some force is applied in upward direction, and below the piston there is a flame, and the boundary between the flame and the gas cylinder is diathermic, and heat can easily pass through this boundary, but the other boundaries are adiabatic, and both the systems are enclosed in a adiabatic boundaries. This is the first case, and in this case we do some work when some heat is applied simultaneously from the flame, and as a result of temperature difference, heat will flow from the body, from the flames having higher temperature toward the gas that is enclosed in the cylinder. If you apply force on the body in the downward direction, so the pressure will increase inside the gas, but if you move or if you allow the gas in the opposite direction, then the piston will move upward. Anyhow, if there is infinitesimal moment of this piston, so as a result of that, some work will be done. So the other example is the paramagnetic sample that has been placed inside liquid helium, and as a result of this, the temperature of liquid helium is low. So the total magnetization of the paramagnetic can be increased by bringing in thermal contact with the liquid helium, because its temperature is lower than the temperature of the paramagnetic solids. So the orientation of this magnetic moment will occur, and the magnetization of the sample will increases. This is one of the case, and in both cases heat is transferred between the bodies, and this heat transfer by virtue of temperature difference. If there is no temperature difference between the two body, and then there will be no net heat transfer between the two bodies. But in both cases we see, even here, the temperature of flame is higher than the temperature of the gas enclosed inside the cylinder, and similarly in the other example, the temperature of liquid helium is lower than the temperature of the paramagnetic solid. So as a result of this difference of temperature, the heat flow will continue, and this heat flow will continue until both the body achieve the same temperature. So in some cases work is done, but in some cases depending upon the external conditions. So we can calculate the work done, and the work done is equal to W is equal to initial final internal energy minus initial internal energy. If we consider an adiabatic process, then in this case the difference between the internal energy will give us the work done, and this is the simple equation what we have developed in the last few lectures. But if we consider non-adiabatic process, so in this case there will be some these two work done will not be equal to the difference between the internal energy, because some sort of energy will be lost due to the friction or due to some unavoidable some circumstances, because 100% energy will not be converted in this case. So energy lost by other means to explain the process is actually the law is actually this contradicts the law of conservation of energy, where the energy goes. So this we can apply on the law of conservation of energy, and this is that when a closed system whose surroundings are at a different temperature in which diathermic work may be done undergoes a process, then the energy transfer by non-mechanical means that is equal to the difference between the change of internal energy and the diathermic is called as heat. So this is actually called as the heat. This is the heat. I mean some sort of energy is lost, and this is heat if we consider diathermic condition. So this is actually this process or the calculation of this difference between the internal energy gives us to a new idea, that is actually the concept of heat, and that also introduced the new mathematical form that will be later on discussed as the mathematical form of the first law of thermodynamics. So if we can move the W, the work done, on the other side of the equation, so what will happen? UF minus UI, that is actually the difference between the internal energy of the systems, is equal to Q plus W. Q is the amount of heat and W is the work done, and in this case we are considering diathermic work. Of course we in most of the cases is actually difficult to have perfect adiabatic process, because in this we may have different sort of energy that is lost due to friction or due to dissipative force or due to resistive forces. So is the concept of adiabatic process is exactly the same like we have considered ideal situation in mechanics or in some other branch of physics. This concept has been only introduced to idealize the simple or simplify the system, and later on we can come to the real situation. So we have two cases for that. If the Q, that is actually the amount of heat, that will be positive when heat enters the system, and it will be negative when heat leaves the system. So heat is actually, Q is actually the amount of heat in this equation. UF minus UI is the difference of internal energy, and W is the work done. So how we can develop the mathematical form of the first law of thermodynamics? For this purpose we have three ideas that are most important to us. The first one is the existence of internal energy function. This is most important, and that was developed in the previous lecture, how the internal energy function develops, and that is most important to us. And the second thing is principle of law of conservation of energy. As I told you in the beginning of the lecture, if some energy is lost, so there is a question where this energy goes. So definitely if the system obey the law of conservation of energy, so this energy must be justified, because in the previous cases we considered that if there is non-adiabatic process, then the difference between internal energy must not be equal to the adiabatic, must not be equal to the work done. So where this energy goes? If the initial energy and final energies are not equal to each other, so a question arises that whether law of conservation of energy holds or not. But definitely law of conservation of energy always holds. So the amount of heat that is missing or that is misplaced or that has been lost, that is due to the heat, and that has been given the name of heat, and that so that is why the law of conservation of energy has been verified. The second thing is the definition of heat as an energy in transit by virtue of temperature difference. Is we discussed that in the beginning of 19th century it was considered that heat is nothing but that is actually a liquid, which was given as the name of caloric or ether by different scientists, and a body having higher temperature have high magnitude of that liquid, and a body having low temperature has low magnitude of that liquid. So that was an old idea or concept about the heat. But now from the first law of thermodynamics we can also consider that heat is nothing but that is actually the form of energy, and it can only transit by virtue of temperature difference. When two bodies have different temperature and they are brought in thermal contact with each other, so heat will flow from a body having higher temperature toward a body having lower temperature, and this heat flow will continue until both the bodies achieve the same temperature. So if we go toward the history of developing the heat as a form of energy, it was not so easy because and many years, decades passed in developing this idea with the help of experimental and theoretical background that heat is a form of energy. So for that purpose several scientists contributed, and today we are going to discuss how many scientists contributed and what are the turning point in developing the idea of heat as a form of energy. So the first thing that what we were considering that heat could not be a fluid within a body was given by Benjamin Thomson. As we discussed before, that heat was considered to be a liquid. Heat was considered to be a liquid, but later on scientists, the first scientist who considered that heat is not a liquid was a Benjamin Thomson, that was actually from America. That he discussed and he argued that heat is not a liquid but actually maybe something else. So moreover, in 1798 Rumford observed the rise in temperature of brass chips produced during the boring of a cannon, and moreover he concluded that the process of boring was responsible for the production of heat, so not some inherent caloric. So later on some other English scientist, that was Sir Humphrey Davy, tried to show that the two pieces of ice could be melted by rubbing them together. His idea was to show that heat is a manifestation of energy, but his experiment was highly conclusive. So further, the most important contribution were made by English scientists, that was actually the Joule. But anyhow, before the English scientists, some other American scientists contribute and some French scientists contributes. One of the French scientists, Seguin, and some in 1839, and some German physician and some German scientists in 1842. His name was Mayer. He also contributed, and they discovered the equivalence of heat and work and made the first announcement of the principle of conservation of energy. But keep in mind, they don't have any experimental observation to prove their ideas. So what happened? The Joule, that was an English scientist, he performed a series of experiments from 1840 to 1849, and he was trying to prove that heat is a form of energy. So his work was published by some scientists, that was the Lord Kelvin, and he refined his work and later on consider that work, of course, heat is a form of energy. Helmholtz, that was actually a scientist, he also contributed to this work, and he had written a paper in 1849 about these ideas. But anyhow, the main turning point in considering heat is a form of energy with experimental background was performed by Joule, and that is why Joule has been his contribution was greatly acknowledged in considering heat is a form of energy. So from that case it was considered that heat is a form of energy. So we can move forward toward understanding the concept of heat. So as we know that heat is either internal energy or enthalpy, and the most important thing when we are discussing about heat is that we have some experimental condition or restriction applied on it. So heat is either internal energy or enthalpy in transit determined by experimental condition. How we have experimental condition for that? If we consider isochoric process or that process, and we consider that volume of the system or volume of the piston remain constant. So in that case all the heat given to the system is converted to the internal energy of the systems. So if we consider some isobaric process is actually the process in which the pressure of the system remain constant. So in that case the heat transfer is called as enthalpy. Anyhow, we will discuss both the cases in detail in the upcoming lectures. But the most important thing is that the heat transfer depends upon the external experimental condition. So temperature difference allow the heat to move from one part of the system to another part of the system. How is possible? If we bring two bodies, two part of the system in thermal contact with each other, and there is temperature difference between the two parts, heat will flow in between these bodies or in between the two parts of the system or two different systems until both the bodies achieve the same temperature. And there is one more important things here need to mention is that the gradient of heat, the heat flow depends upon the difference of temperature. If there is huge difference of temperature, there will be huge heat flow, and if there is small difference of temperature, the heat flow will be slow. So the heat flow continue until both the bodies achieve the same temperature. So this process continue until both the bodies achieve the same temperature. So as we consider that work is not a function of thermodynamic coordinate, just like in the previous chapter, that was the chapter about the work done of different system. In the same way, heat is not also a function of thermodynamic coordinate. So if we consider for the two different system, if we want to know the idea of heat about the and develop the mathematical form of the first law of thermodynamics, so how we do, we consider two objects or two bodies named as A and B, and both the bodies are brought in thermal contact with each other. Keep in mind there is temperature difference exists between the two bodies and the whole system is covered or that has been brought in adiabatic walls. Two bodies named as A and B, they are brought in thermal contact with each other. Both the bodies are placed in or enclosed in adiabatic container or enclosed by adiabatic walls. So as the difference of temperature exists between the two bodies, and the other condition is that both the bodies are brought in thermal contact with each other, so what will happen? The heat will flow from a body having higher temperature toward the body having lower temperature. So if we consider system A, so the heat difference will be given as final internal energy minus initial internal energy, that is equal to the heat lost or gained by the system plus the work done. And if we write the same equation for the second body, that is system B, so that is difference between internal energy is represented by dash, that is internal energy dash UF minus UI dash is equal to Q dash plus W dash. So if we can combine both these equations, so it will be like that UF plus UF dash minus UI plus UI minus into UI plus UI dash, that will be equal to Q plus Q dash plus W dash. Here we can develop some new thing about this equation, that is actually the law of conservation of energy, or even also called as the first law of thermodynamics. So in this case here, the difference between the internal energy of the system, that is UF plus UF dash minus UI plus UI dash, is the change in internal energy of the composite system. W plus W dash is the work done in the composite system, because no heat leaves the systems, no heat goes out from the system, because the system is the system is placed in adiabatic boundary, both the systems. So Q plus Q dash is the heat transfer to the composite system. So as the composite system is surrounded by adiabatic walls, what happen? The Q plus Q dash is equal to 0. So what is the Q is equal to minus Q dash. So it's actually specify that the heat, this is the general conclusion from this experiment of two objects, that Q is equal to minus Q dash. It means that as the whole system is placed in adiabatic boundary, so the heat lost by one object or one body should be equal to the heat gained by other object. And this is also the law of conservation of energy. So heat lost by an object is equal to the heat gained by the object. We have many example from our daily life. Just like if we have placed a hot metal metal strip in water, so the metal strip or the metal rod has high temperature. If we heat it, it's high temperature and the water temperature is low, so the heat flows from the metal rod toward the water, and this heat flow continue until both the bodies achieve the same temperature. Similarly, if we can have many examples from our daily life, which can prove that how the heat is transferred between different objects. So this was something about the mathematical form and heat is the first law of thermodynamics. We will move forward in next lecture about some new topics, inshallah. Thank you very much.